This is the empirical formula, molecular formula, and hydrate worksheet. I want to work out the even problems here to help you understand the process involved if you need some extra assistance here. I hope this helps. Question number 2. Rust or iron oxide can exist as either iron 2 oxide or iron 3 oxide. If you analyze the sample by isolating the iron from the oxygen and found that you had 272.1 grams of iron, which type of iron oxide are you looking at if you started with 350 grams of rust? So the question's telling us that we have this iron oxygen compound and we're looking for the subscripts here. Also, what is given here is that we have 350 grams of the rust, this iron oxide compound. So knowing that we have 350 grams, we can use that information to help us find a couple things. Well, we would know that we have 272.1 grams of iron. So we have 272.1 grams of iron. But what the question does not tell us is how much oxygen. So since we know we have a compound that contains 350 grams of this iron and oxygen containing compound, and we know we have 272.1 grams of iron, it is possible to find out how much oxygen we have by taking the difference of those two. And when we take the difference of those two, the calculator says that we have 77.9 grams. Okay? So once we have that information, we really don't want to focus on this number any longer, and we want to focus in on these two values here. So let's go ahead and find out how many moles, because again, we're looking for the empirical formula. So let's go ahead and erase some of this information here. We'll get rid of that, and we'll take you and move you over here, because that's actually what we're going to look for. So, oops, sorry, you come over here. So I'm going to put you right there. So we'll come back to see what that is. Also, we can move you up here, and we'll move you down here, and we'll take all that, and put you up there. But it looks like this is going to have to be erased, unfortunately. All right, so we have our oxygen, and so let's go ahead and find out how many moles. So we have to find out how many moles of iron we have. And the molar mass for iron is 55.85 grams. So we'll go ahead and put that in there. So 55.85 grams. And then for the oxygen, move that up just a little bit. Okay. So we can find out how many moles of oxygen. And again, remember that it's for oxygen alone. It's not a diatomic. We're not trying, whenever we do empirical formulas, it's for the individual element. We want to find out how many total moles of each element we have. So we're not looking at molecules, we're looking at atoms here. So when you look in your periodic table, you'll find out that oxygen has a molar mass of 16 grams per mole. So we can find out how many moles we have here, because again, we're looking for the smallest whole number ratio. And when I type this information in, for the oxygen, I get 4.869 moles, and for the iron, we get 4.72 moles. Okay, and again, find out which of these two values is the smallest number of moles, and we're going to divide everybody by the smallest number. So in this case, looks like 4.869 is the smallest. And technically, they're very, very close to each other. So 8.69, that equals to 1. 4.869 is like 1.00, a lot of zeros before you see your next number, so it's a 1. So what that means is that we have a 1-to-1 ratio, which means that our iron-oxygen compound looks like this, FeO. Now, the question was wanting you to identify, is that iron 2 oxide or iron 3 oxide? So again, that was the first part of the question. Can it exist as either iron 2 or iron 3? So it wants to know which one have you found. Well, knowing that oxygen has a -2 charge, there's one oxygen, one iron, therefore the charge on the iron must be +2, So we are looking at a sample of iron, Roman numeral 2, oxide. Okay. Some bonus footage here. Question number 3. A form of phosphorus. All right, a bonus footage here. Question number 3 says a form of phosphorus called red phosphorus is used in match heads. When 0.062 grams of red phosphorus burns, 0.142 grams of phosphorus oxide is formed. What is the empirical formula of this oxide? So again, that's kind of some information that really isn't very necessary for this question. Doesn't give us any information, doesn't tell us what the possible formula for this question could be, or for our compound. However, this is pretty important. So it says when 0.062 grams of red phosphorus burns, 0.142 grams of phosphorus oxide is formed. So what we're looking at is we have this phosphorus oxygen compound. And again, so we have this, we're looking for our X and our Y. And it tells us that we have 0.142 grams of this entire compound. Now, it also has given us 0.062 grams of just good old phosphorus. So it doesn't tell us anything about how much oxygen came from the air to combine to form this thing. So again, to find the oxygen, the best thing to do is take the difference of these two. And when we do that, we get a value of of 0.08 grams. Okay? So again, we don't need to worry ourselves about this information any longer. So we're just going to focus on these two things. So actually what I'm going to do is I'm going to move U over. Again, I'm going to be looking for this phosphorus oxygen compound is our final product. We don't need U anymore. And I'm going to take U, move U up, because we have that many grams of phosphorus. So we'll put U there. Put U down here. And we probably can take that and throw that away. So we'll set that. So we have that much oxygen. Okay. So let's go ahead and find out how many moles of each of these we have. So 1 mole of phosphorus, again, has a mole mass of 30.97. So 30.97 grams. And 1 mole of oxygen has a molar mass of 16 grams. So let's find out how much of each of those we have. So for my phosphorus here, I have 0.002, and we'll say 002, and that is moles. For the oxygen, I have 0.005 exactly. Okay, so again, when looking at this, which of these two values is smallest? Obviously the phosphorus. So we'll divide both by the 0.002 and 002. Nice thing is that's a 1, and 5 divided by 2 is 2.5. So we get 2.5. But again, we want to make sure that we have our decimal as a fraction, and 0.5 represents the 1/2. So what we need to do to get rid of this fraction is we just don't round it up or round it down. We have to actually take that into consideration. So to get rid of that fraction or that decimal, we need to multiply everybody by that value there. So when we have this in the denominator, then we got to get rid of it, because we can't have fractions, we can't have decimals, and this is just too large of a decimal to just round. So we'll multiply both by 2. So if you multiply that by 2, you got to multiply the top by 2. So when you do that, Now we get this as a value of 2, and 2.5 times 2 is 5. So when looking at our empirical formula, let's go ahead and scoot that a little bit. So we have P2O5. And again, that only happens because of our fraction here. Now, don't forget, our fractions that we should be like honing in on is the benchmarks for the decimals should be very close to 0, very close to 1/4, very close to 1/3, very close to 1/2, very close to 2/3, very close to 3/4, and then 1. That is the fractional amounts that we're looking for. Now again, if that doesn't ring a bell, obviously this is 0.25, this is 0.3 repeating, this is 0.5, this is 0.6 repeating, and this is 0.75. Now, the good news is what I will never do to you is I will never give you a value that if you calculate it correctly, you won't get like a decimal of 0.29. That's not going to happen. And if you do, you messed up on your calculation. So you should get something that's really close to one of these quote-unquote decimal benchmarks when doing your mole fractions. Don't round too much. In other words, when you're working this problem out, don't even consider and go, 2.5, I'll just round that up to 3. You round that up to 3, now we got a 1-to-3 ratio versus a 2-to-5. Extremely different. So be careful, don't do too much. And again, these are our benchmarks that we're looking for when working out empirical and molecular. Number 4 says a compound is composed of 7.2 grams of carbon, 1.2 grams of hydrogen, and 9.6 grams of oxygen. And whenever they list elements in that has more than one, or any list of elements, keep them in that same order. Don't get creative and go, I want to put hydrogen first. If it goes carbon, hydrogen, oxygen, that's what your formula should look like. Continuing on, the molar mass of the compound is 180 grams. Find the empirical and molecular formulas for this compound. So when looking at this, let's see here, we have some information. We have a carbon, hydrogen, and oxygen compound, and we're actually looking for these values here. So we want to know what is the X, Y, and Z for this carbon, hydrogen, and oxygen compound. So let's go ahead and move those over. So we'll come back to that. Get you guys over there too. So we're going to find out what those values are here in a moment. So again, let's list them in the order that we were given. So 7.20 grams of carbon. We have, let's get that down, 1.2 grams of hydrogen. And again, it's just a single hydrogen. We don't have H2 here. And let's see here. And also we have 9.6 grams of oxygen. So 9.6 grams of oxygen. Okay. And from the periodic table, carbon has a molar mass of 12 grams per mole. Sorry, 12.01 grams. The hydrogen has a molar mass of 1.008 grams, and again, not H2. And the oxygen has a molar mass of 16 grams per mole. So let's find out how many moles of each of these we have, and then we can find out what our values are here. 0.5995 moles of carbon, 1.1, we'll say 90 moles of hydrogen, 0.6 moles of oxygen. Okay, so here are our values, our mole amounts. Again, let's divide it by the smallest whole number. So in this case, looks like the 0.59, but technically the 0.6. They're very, very close to each other, but I'll go with the 5995. So that is one of those, and definitely one of these. Again, it's that scenario where it's 1.0, a lot of values until we get our next number, but round it, it's very, very close to 1. When looking at this one, 5995, I believe that one is a 2, very, very close to 2. So it's like a 1.9 something. So let's see here, double check that. Yeah, 1.98578. So here are our values. So it's a 1 to 2 to 1 ratio. So I'm looking at the empirical formula, we will have CH, let's go ahead and put a 2 in there. Oh, so there's your empirical formula for this carbon, hydrogen, oxygen compound. Now the question also wants us to find the molecular formula. So this is the empirical formula. We'll go ahead and put that in there. And now we need to solve for N. In other words, the multiplier. Carbon, hydrogen, oxygen compound. So what we need to do is find out what our value for N is. And as a reminder, N represents the molecular formula mass over the empirical formula mass. Now the nice thing is the molecular formula mass for you guys will be given. So in this case here, the molecular formula mass is 180 grams. Very nice. So we can go ahead and plug that in. So we know that that's 180 grams. Now you have to decide what the empirical formula mass is. So to do that, you have to look at how many of each of the elements you have and determine that. So carbon 12.01 plus 2 hydrogens, which is 1.008, plus 1 oxygen, which is 16. And when I type all that in, I get something very close to 30. So 30 point something. It's like 30.026. So again, remember our N has to be a whole number, and it would be something like 5.999 something. So in this case, we are looking at a multiplier of 6. So since our N has a value of 6 here, our empirical formula, let me zip it down here, our empirical formula will be, again, you're going to multiply the 6 by everything in the box. So you have C6, H12, O6. And I hope that you all come to know that molecule. That should be something that you learned back in biology. That's glucose. That's a very familiar sugar. Okay. Number 6. In areas where temperatures get extremely cold, people must take special precautions to make sure machinery runs properly. One compound contains 83% rubidium, 16% oxygen, and 1% hydrogen is used as a low temperature storage, is used in low temperature storage batteries. What is the empirical formula for this compound? So again, keep it in the same order. So again, we have 83% rubidium, so we're looking at a rubidium, and then a 16% oxygen and a 1% hydrogen. So what we're looking for here, X, Y, and Z. Now, we have our percentages. Probably the smartest thing to do is to treat those percentages as a 100 gram sample of this rubidium, oxygen, hydrogen compound. So that means we're going to have 83 grams of rubidium, 16 grams of oxygen, or 1 gram, and 1 gram of hydrogen. Now you can pick any number that you want as your total mass, but using 100 is very, very nice and very easy to work with. So this is what we're going to look for over here. So let's move you over there. Okay, I'll put that right there. Now rubidium, let's find out what the molar mass for rubidium is. It's a group 1A metal, and it's just right there. Looks like I need to move down just a little bit. So rubidium has a molar mass of 85.47 grams per mole. And what was the percentage again? 83, that's pretty good. So we have 83 grams of rubidium. And let's see, what was that molar mass again? 85.47, so 1 mole is 85.47 grams. So find out a number there. Oxygen, we have 16% or 16 grams of oxygen. So we'll go 1 mole of oxygen, which is 16 grams. Well, I can do that in my head. That's all 1 mole. That's nice and easy. And then looking at the Hydrogen, we had a 1%, so that means 1 gram of hydrogen. And that's pretty close, but I don't want to round it too much here. So let's find out what those 0.99, so it's 0.97, say 1. Okay, so what we'll do is we'll divide each of these out, and let's see, the smallest one looks like this one, so there's a 1, and over there, and that'll be very close. So 1.02, we'll talk about that here in a second. Actually 1.03, sorry. It's 1.02 as well. Alright, so now let's talk about this. Okay, we have some numbers that are very, very close to 1. And our targets that we're shooting for, again, remember, especially when changing these decimals into fraction, it starts at 1/4. So we go from 0 to 1/4 to 1/3 to 1/2 to 2/3 to 3/4 to 1. Okay, so when looking at this, these values are nowhere near 0.25. They're closest to 0. And when we look at these fractions, they're nowhere near that. So we're just going to say that these are all values of 1, which is sometimes some people get upset by that, but unfortunately that's what the answer actually is. So our formula is RBOH because those all have a representative 1. So our mole ratios are very, very close to 1. Now again, what we don't want to do is round too much. So if you had, and again, hypothetically speaking, we're finished with this question already. If you had, say, 1.25 as your mole amount, or your mole ratio amount, then we would want to make sure that we do some multiplication on these other ones. But we did, so that's good. Okay. Let's look at the next one. So number 8, it asks, what is the formula for the hydrate that is 76.06% La2CO3 parentheses 3 and 23.94% of water? Now again, whenever I'm giving you the compound or the compound's been given to you, keep it together. And we want to find out how many moles of this, because again, this is a hydrate. And we're looking for a value for the water. And as a heads up, and to make sure you're doing it correctly, this value should always be a 1, and the water will have a value that could be 1 or greater. So let's go ahead and take these percentages and make them into grams. So again, we have 76.06 grams of our La2, CO3, 3. And we'll find out what the molar mass of that is here in a moment. And then we'll do our 23.94 grams of water. And water has a molar mass of 18.016 grams per mole. Once you've worked with water a long time, you'll figure that out real quick. But this one, that one's a little bit different. I'll have to figure that one out. So we had 2 LAs, 2 lanthanides, and lanthanide's right there. So lanthanide 138.91. So let's get that 138.91. So 1 mole. So we have 2 of those. 138.91. Plus we have 3 carbons, so 12.01, and we also have 3 times 3 or 9 oxygens. Okay, let me find out what the molar mass of that is on the bottom here. The molar mass of this lanthanide compound is 457.95 grams. Okay, so let's find out how many moles that actually equates to. So let's move it down here. So 0.166 moles. And the water, 2. Okay. So obviously the 0.116 moles is the smallest. And again, as I had stated, we want to make sure that this value has a 1. So that obviously is a 1. And then we'll divide that by 0.66. Let's get that number down here. 8 point, with a lot of zeros. So 8.0, quite a few zeros. So it's a 1 to 8 ratio. So our formula looks like this. We have 1 La2 carbonate. And then we put this dot here. Okay, that dot is representing a hydrate. Let me move that down just enough. That dot represents a hydrate. So it's not a multiplier, it just tells us simply that we have water chemically attached to this compound. And since there's 8 water molecules, then that means we will put an 8 there. So we have an 8 for our water. Okay? So our answer is that right there. And this is our hydrate, formula for the hydrate. Now if you were to find the molar mass for this, you would find out, like what we did here, down here, so the 457, and this actually is acting as a plus sign. So it means that there's 8 water molecules chemically attached to that.
Isn't that cool?
Awesome.